The Milankovitch cycles, Earth's movement, and cosmic influences on climate. A comprehensive guide. Earth's climate is shaped by a grand cosmic dance, the Milankovitch cycles. These subtle shifts in our planet's orbit, tilt and wobble, driven by celestial forces, have orchestrated ice ages, warm periods, and everything in between. But what do these ancient rhythms mean for our planet today? Could they hold the key to understanding modern climate change? Or even predict the next big shift? And how do other cosmic influences, like solar flares or asteroid impacts, fit into the picture? Let's unravel the mysteries of Earth's movements and their profound impact on our ever-changing world. The Milankovitch cycles, named after Serbian scientist Milutin Milankovitch, describe the collective effects of changes in Earth's movements on its climate over thousands of years. Milankovitch's groundbreaking work provided the first mathematical explanation linking Earth's orbital variations to long-term climate changes, revolutionizing our understanding of glacial and interglacial periods. These cycles are primarily driven by variations in Earth's orbital eccentricity, axial tilt, obliquity, and precession. They influence the distribution and intensity of solar radiation reaching Earth's surface, thereby playing a significant role in triggering glacial and interglacial periods. Expanding beyond these cycles, Earth's movement within the solar system, the Milky Way galaxy, and the broader universe introduces additional factors that shape the planet's environment and long-term evolution. Earth's daily rotation is more than just the passage of time. It's the heartbeat of our planet. From the split-second precision of atomic clocks to the gradual lengthening of days over millions of years, the story of Earth's spin reveals a dynamic and evolving system. But what causes these changes? How does our rotation influence life, weather, and even the tides? And could we be on a slow march toward days that feel endlessly long? Let's dive into the fascinating world of Earth's daily rotation, from seconds to days, and uncover the secrets of our spinning planet. Earth's rotation on its axis is a marvel of motion, creating the familiar cycle of seconds to 24 hours that defines our days. This steady spin drives the alternation of day and night, influences weather patterns, and shapes ocean currents. But how does this timescale stay so precise? What mechanisms keep our planet spinning? And what subtle forces are at play to gradually slow it down? Explore the profound effects of Earth's rotation on life, the environment, and the delicate balance of time itself. Earth's rotation on its axis not only determines the day-night cycle, but also profoundly influences the planet's energy balance. By regulating the distribution of solar energy between day and night, this rotation drives temperature variations, weather systems, and the rhythms of life on Earth, showcasing the intricate connection between time and the energy that sustains our planet. The rotation of Earth sets the rhythm of day and night, shaping the flow of time and energy across the planet. This consistent motion profoundly affects ecosystems, fueling processes like photosynthesis in plants, guiding nocturnal activities in animals, and triggering seasonal behaviors critical to the balance of life on Earth. The rotation of Earth drives the cycle of day and night, regulating diurnal temperature fluctuations that influence weather patterns, climate systems, and the survival strategies of countless organisms. The rotation of Earth underpins the planet's energy balance, ensuring the distribution of solar energy between day and night, which is essential for maintaining climate stability and supporting life. Earth's orbit around the Sun, spanning months to a year, is the cornerstone of our planet's seasonal rhythms and ecological balance. This elliptical journey, combined with the tilt of Earth's axis, drives the temperature shifts and weather patterns that define life as we know it. But what makes Earth's orbit so unique? How do subtle changes in its shape and speed influence our climate over time? And what role do other celestial forces play in shaping this cosmic dance? Let's explore the fascinating mechanics and impacts of Earth's annual journey around the Sun. Earth's orbit around the Sun spans approximately 365.25 days, a timescale that defines our year and shapes the planet's seasons. This precise journey, influenced by the tilt of Earth's axis and its elliptical path, regulates the cycles of life, weather, and climate, creating the intricate patterns that sustain our world. Earth's annual journey is governed by its elliptical orbit around the Sun, a path dictated by Kepler's laws of motion. This mechanism ensures that Earth moves faster when closer to the Sun and slower when farther away, creating variations in solar energy that influence seasonal changes and the balance of life on the planet. Earth's elliptical orbit, combined with its axial tilt of approximately 23.5 degrees, is the driving force behind the changing seasons. As the planet travels around the Sun, solar insolation, sunlight reaching Earth's surface, varies between solstices and equinoxes. This variation causes the temperature shifts that define seasonal patterns, shaping ecosystems, weather systems, and the rhythms of life. Milankovitch cycles, long-term changes in Earth's orbit, tilt, and axial wobble drive profound shifts in climate over thousands of years. These subtle variations influence the distribution of solar energy, shaping ice ages, warm periods, and the planet's long-term climate dynamics. Axial precession, or Earth's wobble, follows a 21,000-year cycle that gradually shifts the orientation of the planet's axis. This slow movement alters the timing of the seasons relative to Earth's orbit, influencing long-term climate patterns and contributing to cycles like glaciation and interglacial periods. Axial precession alters the timing of the seasons relative to Earth's orbit, shifting when solstices and equinoxes occur. This gradual change modifies the intensity of seasons in each hemisphere, amplifying or diminishing temperature contrasts over millennia and influencing long-term climate dynamics. Obliquity, or the tilt of Earth's axis, varies over a 41,000-year cycle, shifting between approximately 22.1 degree and 24.5 degrees. This variation plays a crucial role in shaping Earth's climate by influencing the distribution and intensity of solar energy across the planet, particularly at higher latitudes. Obliquity refers to the oscillation of Earth's axial tilt. This change is driven by gravitational interactions with the Sun, Moon, and other planets, subtly altering the angle at which sunlight strikes different parts of Earth. Greater axial tilt amplifies seasonal intensity, leading to hotter summers and colder winters, while a smaller tilt reduces these extremes, creating more moderate seasonal variations. For example, during periods of higher obliquity, regions such as the Arctic experience significantly warmer summers, leading to substantial ice sheet melting and contributing to interglacial periods. A lesser axial tilt moderates seasonal extremes, resulting in milder summers and winters. This reduced tilt also enhances the stability of polar ice and plays a critical role in driving glaciation cycles over thousands of years. Orbital eccentricity refers to the shape of Earth's orbit, which varies from nearly circular to slightly elliptical over a 100,000-year cycle. These subtle changes in orbital shape influence the amount of solar energy Earth receives throughout the year, playing a key role in long-term climate patterns and glaciation cycles. Orbital eccentricity changes result from gravitational interactions with Jupiter and Saturn, which affect the shape of Earth's path around the Sun.
Milankovitch, a scientist so grand, he studied Earth's movements, the climate's guiding hand. Orbital variations, the cycles so profound. Glacial ages come and go, the evidence is found. Eccentricity, obliquity, and precession too, a cosmic rhythm guiding what the Earth will do. From glaciers cold to interglacial blooms, Milankovitch cycles play their timeless tunes.
Orbital eccentricity affects the distance between Earth and the Sun throughout the year, altering the amount of solar energy the planet receives. During more elliptical orbits, seasonal contrasts can become more pronounced, intensifying climatic extremes. Conversely, near-circular orbits lead to more uniform solar energy distribution, moderating seasonal variations. Additionally, orbital eccentricity amplifies or dampens the effects of axial tilt and precession, further influencing long-term glaciation cycles and climate patterns.
100,000 years, the orbit shaped has changed, from nearly round to stretched, it shifts within its range. Solar
Scientific literature on the Milankovitch cycles provides a wealth of evidence linking Earth's orbital variations to long-term climate changes. These studies explore how shifts in eccentricity, axial tilt, and precession influence solar insolation, triggering glacial and interglacial periods over millennia. Research highlights the critical role of these cycles in shaping Ice Age dynamics, the distribution of ecosystems, and even ancient human migration patterns. Contemporary investigations also examine how the Milankovitch cycles interact with modern anthropogenic climate change, offering insights into the interplay between natural and human-driven forces shaping Earth's climate. Key findings from paleoclimatology, geology, and astronomy converge to deepen our understanding of this intricate cosmic and terrestrial connection.
It shifts the seasons in. The timing of the solstice changes through the years. Precession plays a subtle tune that all the earth reveres. Eccentricity, obliquity, and precession too. A cosmic rhythm guiding what the earth will do. From glaciers cold through interglacial blooms, Milankovitch cycles play their timeless tunes.
NASA Science provides an in-depth explanation of Milankovitch cycles, highlighting their significance in driving Earth's long-term climate variations. Through detailed analysis, NASA explains how changes in Earth's orbit, tilt, and wobble affect solar energy distribution, leading to the onset and retreat of ice ages. By integrating paleoclimate data with cutting-edge modeling techniques, NASA offers a clear understanding of how these cycles interact with other climatic factors, shedding light on the intricate mechanisms shaping Earth's climate over millennia. Academic research, such as the study Long-Term Changes in the Earth's Climate, Milankovitch Cycles published in the American Journal of Physics, explores the mathematical foundations of Milankovitch cycles and their correlation with climatic shifts. These studies provide detailed analyses of how orbital variations influence solar insolation, driving long-term changes in Earth's climate. By combining physics, paleoclimatology, and advanced modeling, this body of work deepens our understanding of the mechanisms behind glacial and interglacial periods, offering valuable insights into Earth's dynamic climate history.
Climate bends, Milankovitch cycles, the story extends. Jupiter and Saturn, pulling from afar, they shape our orbit, guiding who we are. 1 billion years of stability and play, the solar system's harmony will sway. Earth moves in the solar tide, galaxies turning where stars reside. From the sun's embrace to the Milky Way.
Understanding Milankovitch cycles begins with rigorous academic research, such as the study Long-Term Changes in the Earth's Climate. Milankovitch cycles published in the American Journal of Physics. These works provide a mathematical foundation for the cycles, detailing their derivation and exploring their correlation with long-term climatic shifts. By combining physics and paleoclimatology, these studies deepen our knowledge of how orbital variations influence solar energy distribution and drive glacial and interglacial periods. Visualization tools like Earth Orbit v2.1 add a dynamic layer to this understanding, offering 3D models of Earth's orbital mechanics, Milankovitch cycles, and insolation patterns. These interactive tools enable scientists and educators to analyze the interplay of these factors across geological timescales. Complementing this are paleoclimatology insights from studies like Filtering of Milankovitch Cycles by Earth's Geography, which examine how Earth's geographical features modulate the effects of these cycles, providing a historical context for understanding past climate variations. The Copernicus dashboard complements this academic foundation by offering tools and data for applied analysis. As part of the European Union's Copernicus program, it provides access to satellite observations, visualizations, and research articles, such as filtering of Milankovitch cycles by Earth's geography. These resources help scientists and educators examine how Earth's geographical features modulate the climatic effects of orbital variations, offering valuable insights into past climate patterns and their implications for the future. Paleoclimatology insights build on the tools and data provided by platforms like the Copernicus dashboard, using them to reconstruct Earth's climate history and understand long-term patterns. Research such as filtering of Milankovitch cycles by Earth's geography examines how the planet's physical features, like the distribution of continents and oceans, modulate the effects of orbital variations. These studies shed light on how past climates were influenced by the interplay between geography and Milankovitch cycles, offering critical perspectives on the mechanisms driving glaciation, interglacial periods, and broader climatic shifts over geological timescales. These studies shed light on how past climates were influenced by the interplay between geography and Milankovitch cycles, offering critical perspectives on the mechanisms driving glaciation, interglacial periods, and broader climatic shifts over geological timescales. Cambridge University Press. Evolutionary Impacts. The study Milankovitch cycles and their effects on species in ecological and evolutionary time delves into the profound influence of climate changes driven by orbital variations on species evolution and distribution. These cycles have shaped ecosystems over millions of years, driving migration patterns, altering habitats, and playing a pivotal role in speciation and extinction events. By linking geological timescales to biological processes, the research provides a deeper understanding of how Earth's orbital mechanics have fundamentally shaped the course of life on the planet. Recent studies have expanded the understanding of Milankovitch cycles beyond the Quaternary period, delving into Earth's deep time climate history. The study Milankovitch forcing in deep time explores astronomical solutions spanning the past 3.5 billion years. By providing templates for interpreting deep time cyclostratigraphic records, this research offers critical insights into ancient climate patterns and helps refine external forcing functions in modern climate models. These advancements bridge the gap between geological timescales and contemporary climate science, enhancing our ability to model and predict Earth's climatic future. The study Obliquity and Precession as pacemakers of Pleistocene deglaciations, published on arXiv, employs a Bayesian approach to model ice volume variations during the Pleistocene epoch. This research underscores the dominant role of Earth's obliquity in pacing glacial cycles, providing a more detailed understanding of how orbital variations influence long-term climate dynamics. By refining our grasp of these mechanisms, the study contributes valuable insights into the complex interplay between Earth's movements and glaciation processes. Glacial cycles pause, disruptive we see nature's rhythm altered by humanity. But in the future, without a trace, ice will return to reclaim its space. 50,000 years, a new ice age waits. Earth's movement within the solar system is fundamental to its climate, stability, and long-term environmental dynamics. Its orbital motion around the sun not only defines the seasons, but also regulates the annual distribution of solar energy, driving the Milankovitch cycles that shape long-term climate trends. Gravitational interactions with other planets, particularly Jupiter and Saturn, further influence Earth's orbital eccentricity and stability over millions of years, highlighting the complex interplay of forces that govern our planet's place within the solar system and beyond. Bound by gravity, a universe in flight. Andromeda's coming, its beauty near, colliding galaxies in 4 billion years. Local group, a cluster of light, bound by gravity, a The solar system's galactic orbit around the center of the Milky Way, completed approximately every 225 to 250 million years, profoundly impacts Earth's atmosphere and climate. Variations in cosmic ray flux, influenced by the solar system's position within the galaxy, can alter atmospheric chemistry and cloud formation, potentially shifting global temperatures. Encounters with dense interstellar gas and dust further modify the heliosphere, increasing Earth's exposure to cosmic radiation and triggering atmospheric changes. Additionally, periodic movements through the galactic plane may correlate with mass extinction events, driven by heightened comet activity or increased radiation exposure, underscoring the interconnectedness of Earth's fate with its journey through the galaxy.
Galaxies turning where stars reside. From the sun's embrace to the Milky Way spin, the rhythms of space show where we've been.
The interstellar medium plays a significant role in shaping Earth's environment as the solar system traverses regions of dense interstellar gas and dust. During these encounters, the heliosphere, the protective bubble formed by the sun's magnetic field, is compressed, increasing Earth's exposure to cosmic radiation. This heightened exposure can impact atmospheric conditions, alter climate patterns, and potentially trigger biological or environmental changes on a planetary scale, highlighting the profound influence of the interstellar medium on Earth's history and future. Mass extinctions in Earth's history may be linked to periodic movements through the galactic plane. These transitions can increase comet activity from the Oort cloud, raising the likelihood of impacts, or expose Earth to intensified cosmic radiation. Such events have the potential to cause dramatic shifts in climate and trigger widespread biodiversity loss, underscoring the connection between Earth's position in the galaxy and major evolutionary turning points.
Its great attractor pulling through the cosmic halls, yet the universe expands, a dance so grand. Galaxies drifting, the cosmos unplanned. Ice reflects the warming sun. Greenhouse gases block the fun. Cosmic forces shape our fate. Feedback loops, it's never too late. CO2 rising, a human-made feat from 280 to 420. The Earth feels the heat, glacial cycles pause.
Cosmic context highlights Earth's place within the vast dynamics of the universe, including the Milky Way's movement within the local group. The galaxy's gradual approach toward Andromeda, its largest neighbor, has the potential to influence long-term stellar interactions and even alter planetary trajectories. While these changes occur over billions of years, they provide a fascinating glimpse into the interconnected movements of galaxies and their potential ripple effects on solar systems like our own. While these changes occur over billions of years, they provide a fascinating glimpse into the interconnected movements of galaxies and their potential ripple effects on solar systems like our own. Laniakea supercluster situates Earth within a vast cosmic framework, as the local group moves toward the Great Attractor at an astonishing speed of approximately 600 km/h. This motion offers valuable insights into the structure and dynamics of large-scale cosmic formations, such as galaxy clusters and superclusters. However, despite its immense scale, this movement has negligible direct impact on Earth's environment, serving more as a testament to our place in the universe's grand design. The forces of gravity counteract the universe's expansion. As a result, while galaxies outside this group continue
Galaxies turning where stars reside. From the sun's embrace to the Milky Way spin, the rhythms of space show where we've been. The local group, a cluster of light.
The interaction between Milankovitch cycles and cosmic movements underscores the complexity of Earth's climate system. Feedback mechanisms like the ice albedo effect, where increased ice cover reflects more sunlight and promotes further cooling, and greenhouse gas feedback, where cooler oceans absorb more CO2 and enhance cooling, amplify the effects of orbital variations. Additionally, cosmic influences such as galactic movements and interstellar interactions can modulate Earth's long-term climate trends by altering radiation levels or triggering extraterrestrial impacts, highlighting the dynamic interplay between terrestrial and cosmic forces in shaping Earth's climate over geological timescales. Current and future implications. Human activities are profoundly altering Earth's climate, potentially overriding natural cooling trends driven by Milankovitch cycles. The unprecedented rise in atmospheric CO2 levels, now exceeding 420 ppm due to anthropogenic greenhouse gas emissions, is driving warming trends that disrupt the natural progression of glacial cycles predicted by these models. This human-induced warming not only challenges the delicate balance of Earth's climate system, but also raises urgent questions about the long-term implications of our actions on the planet's future stability and habitability. Future glaciation. Without human interference, Earth's natural climate cycles suggest the planet would likely enter a new glacial phase in approximately 50,000 years. This prediction, based on Milankovitch cycles and long-term climate trends, highlights the profound impact of anthropogenic activities, which may delay or entirely disrupt this natural progression by significantly altering atmospheric CO2 levels and global temperatures. Galactic evolution. Over billions of years, the solar system's changing position within the Milky Way will likely continue to shape Earth's cosmic environment. These gradual shifts, including encounters with different regions of interstellar gas and dust or movements through the galactic plane, could influence radiation levels, atmospheric conditions, and even the potential for extraterrestrial impacts, underscoring the dynamic interplay between Earth and its evolving galactic surroundings. In conclusion, Earth's movements, ranging from its daily rotation and orbit around the Sun to its vast journey through the Milky Way, create a dynamic system that shapes the planet's climate and environment. The Milankovitch cycles serve as a crucial framework for understanding long-term climate changes, while the broader cosmic context, including galactic interactions and interstellar influences, adds layers of complexity to this intricate web. By studying these interconnected processes, we not only uncover the story of Earth's past and future, but also recognize the critical need to balance human activities with natural cycles to ensure a sustainable future for our planet. And so, Earth's story is one of movement, rotating daily, orbiting the Sun, and journeying through the vast expanse of the Milky Way. These motions, from the subtle shifts of Milankovitch cycles to the grand scale of galactic interactions, weave together the delicate balance that shapes our climate and environment. As we look to the future, understanding these forces reminds us of the intricate connection between our actions and the natural rhythms of the universe. The challenge and opportunity is ours, to live in harmony with these cosmic patterns and ensure a thriving, sustainable planet for generations to come. Thank you for joining us on this journey through Earth's movements and their cosmic connections. If you enjoyed this exploration and want to uncover more about our planet and the universe, don't forget to like, share, and subscribe to the channel. Hit the bell icon so you'll never miss an update, and let us know your thoughts or questions in the comments below. Together, let's keep exploring the wonders of our world and beyond. See you in the next video.
Years, galaxies turn, the planets sway, continents drift and oceans play, cycles stable, fossils